Bismillahirrahmanirrahim. Assalamu alaikum. Today we are starting with the lecture number 32nd, and this will be the last lecture. And during this lecture we will cover the topic that is called the Intel x86 instruction encoding. Now before that we have discussed so many topics. We have covered almost all the course syllabus. Now before that we have covered the syllabus, and this is the topic that we are going to cover during this lecture. And during the previous lectures we have seen that we programmed in assembly language. Now we will see what is going to be transferred directly to the computers, like when we are going to write ADD instruction, subtract, increment, decrement, and so on, all other instructions. Then what will be actually being transferred, like in binaries or in hexadecimal, whatsoever the representation is, to the computer, so that computer performs its operation accordingly. Now this is the lecture outline. Now here we will see first we are going to encode real x86 instructions. For example, we have ADD instruction. So this ADD instruction along with like EAX, EBX. So for example, whenever you write this instruction, what will happen, or what type of code, or what is the pattern, bit pattern that will be transferred? For example, 0 0 0 1, or like this one, and so on. So we can say 0 1 is being transferred, or 0 2 is being transferred, and so on. All the other bits are being transferred to the computer, so that computer can match with its instruction set architecture and act accordingly. So the control signals are generated based on this code and so on. Now after that we will discuss about the x86 instruction format reference. What is x86 instruction format? Mean the bit pattern inside the x86 instruction format. Then sizes of the opcode. What is the basic size of opcode? Either it is 1 byte, 2 byte, or more than these two, more than that one. But actually it is 1 byte, or maybe it can be 2 byte, only the opcode. Then so this part here, for example, add, increment, compare, or all the other instructions, this is the opcode part. So this opcode is represented either in 1 byte or maybe in 2 bytes. So after that we will discuss about the x86 ADD instruction opcode. We will take only one instruction, ADD instruction. There are so many instructions and there are so many formats of this instruction. Similarly, you can follow, you can take any other instruction, and there are different addressing modes. You can apply all the addressing mode. For example, here we are using register addressing mode, and if we are using the this is 32-bit register addressing mode. Similarly, if we are using the 8-bit addressing mode, AL, BL, and so on, or maybe you want to use 8 EAX, 20H. This one is the for example, immediate addressing, or sometimes you are using displacement and so on, base register, base index, or index scaling mode, and whatsoever the instruction mode you are using. Now after that we'll see how we can encode x86 instructions, instruction operands, along with the MOD-REG-RIM byte. So this MOD-REG-RIM byte is 1 byte information, and how this 1 byte information is being treated, like what is the meaning of first 2 bits, then next 3 bits, and then next 3 bits, and so on. Then we'll see what is the register field of the MOD-REG-RIM byte, or basically we call it MOD-RIM byte, or mod addressing byte, whatsoever you can call it. So MOD-RIM byte and addressing modes will be discussed precisely here. Then we have the scale index and byte, scale index byte, this is called the SIB, or scale index byte. This one is also 1 byte information, and this 1 byte inside the whole instruction has a special meaning. When you are using scale indexing mode, then this byte will work there. After that we are using the layout of the scale index addressing mode, and so on. And then we will see the examples of ADD instruction, multiple examples like ADD CL, AL, or the other. You can change all these registers and so on. Then 32-bit registers, then EDX plus displacement, EDX plus EBX, this indirect addressing, then ESI plus base displacement, and so on. So there are different formats, and the last one is the ADD immediate instruction. Now these are the examples we will see throughout, we will carry on throughout the whole this course. However, this ADD instruction is not the only instruction inside the instruction set. There are so many other instructions, and you can see the reference manual from the Intel Corporation. The opcodes are for all the instructions are available. For example, here ADD has a special opcode. Similarly, move has a special opcode, increment has a special opcode, and so on. So you can see the manual, or if you don't want to see the manual, then definitely you can directly go to the project when you are going to run in the step over mode. So you can right click and go to disassembly. So when you press F10, so it will continue in step-by-step mode, and then you can right click. So when you right click, after that you can have the go to disassembly and so on. So disassembly, so on. When you press go to disassembly, you will see the complete hexadecimal representation of this instruction, or whatsoever the instruction you are using. For example, if you are using ADD instruction or some other instruction, whatsoever the format you are using, it will be displayed inside the disassembly and so on. So now we are going to carry out with the lecture outline. So the first one is the encoding the real x-axis instructions. So now we have already programmed our in assembly language. Now this is the time then that we are going to look at the actual machine instruction format, means how machine instruction format is being supplied to the microprocessor or the x86 CPU family, so that it is performing actions. They don't call the x86 CPU a complex instruction set for nothing, because it is really a very complex instruction set. On the other hand, if you just go to the RISC instruction set, in this course mostly we covered the CISC part, CISC instruction set format. However, if you just go to RISC, it is very simple. So that is the reason this is called reduced instruction set computer and whatsoever. So reduced instruction set computer, there are only 32 bits. So this whole 32-bit is divided into, for example, opcode and other options in 32-bit in the RISC format. So we have covered the Intel x86 CPUs and the Intel x86 assembly language and so on. So now we are going to discuss about what is inside the CISC and how instructions are being encoded when we are using the Intel architecture computers and Intel architecture instruction format. There are more complex instruction inside this this architecture, and there is no challenge about that one. And the x86, the Intel architecture, or IA, mostly you will find like Intel architecture is IA and so on. So IA 32-bit or 64-bit, 16-bit and so on. It has the most complex instruction encoding, the most complex one that you can ever find if you compare with the RISC. So here you can see there are prefix bytes. So for example, there are 4 prefix bytes, 1, 2, 3 and 4. So these are the bytes, like 1, 2, 3 and 4 bytes. Then we have the 2-byte opcode and so on. So in the prefix byte can be either 0, means some instruction either use prefix bytes, like maybe they are using 1 byte, 2 byte, 3 or 4 bytes. However, some instruction doesn't use this prefix byte. So that will also a fact that it has a special meaning when we are using the prefix byte. After that, we have 2 byte, 1 or 2 byte. It is necessary that there should be 1 or 2 byte opcode. This 2 bytes opcode is used to represent what type of operation is being performed by the instruction, like the ADD instruction, ADD immediate, move immediate, and so on. Whatsoever the operation you are going to imagine, or whatsoever the instructions you have encoded are written inside assembly language, all those instructions have unique combination. So for example, if I say, if you combine all those instructions, all those bytes, then you will never get any 2 instructions they have the similar bit pattern. It's impossible. Then the possibility is that if 2 instructions, 2 different instructions have similar bit pattern, or for example 2 different instructions are going to produce 3C, DE, F1 for example, then 3C is like 0, 0, 0, 1, 1, C is 1, 1, 0, 0, and so on. So this is the bit pattern which is supplied, or which is transferred, or which is given to the microprocessor, and the microprocessor will act accordingly according to this bit pattern. Now if 2 instructions have the similar bit pattern, then how a microprocessor will distinguish that which action it has to perform? However, there is possibility that one instruction can have 2 different bit patterns, but basic bit pattern should be similar. Here you will see inside this one that one instruction can have 2 bit patterns. However, in assembly language, when you are going to encode, it has proper format, and it will just show you the only bit pattern that you are going to use. So we have 2 bytes, 1 or 2 bytes for the opcode. Then we have 1 byte for the register MOD-REG-RIM byte. So this byte specifies the addressing mode and instruction operand size. So sometimes the middle 3 bits, which are going to show register, they are being used as a part of instruction. That is the reason you will see when we are going to study it in more detail that this is called register/operand byte. Register/operand byte. So these 3 bits are of this 1 byte. So there are 8 bits here. So out of that, mod is 2 bits. Register or operand is 3 bits. RM is also register is also 3 bit. So 2 bits here, then 3 bits, and then 3 bits, and so on. So 3 bits, 3 bits, and 2 bits. So it is divided in such a way, starting from the least significant bit here, for example, and most significant bit here, and so on, whatsoever the bit pattern is. Now this byte will identify the addressing mode and the instruction operand size, whatsoever you are what type of operands you are using. The next byte is called the SIP byte, scale index byte. The short form is SIP byte. Not all the not all the instructions are using SIP byte. However, it's available. So this is the optional scale, and that is the reason we call it optional. So this is the optional scale index byte. If the instruction uses a scale index memory addressing mode, for example, we are using the arrays. So we have array name, we have the index register, and for example, sometimes we have base index and multiply by 1, 2, 4, 8, and so on, whatsoever we multiply the value of n and so on. So it has so many representations. So if you are using this type of instruction mode, or the addressing mode, sorry, then this byte will be used. So this byte is also 3 byte, or this byte is also there are 8 bits inside this byte. Now inside this byte there are 2 bits for the scale and index and base, 3 bits, and so on. We will see it in more detail. And after that we have the displacement of 4 byte. If you are using displacement, then there will be 4 bytes for displacement. And if you are using immediate or constant data, That can be, for example, if I want to perform 8 and then I have some register here and I have some hexadecimal value, or some other instructions in RISC, they have the ADI or add immediate and so on, or ADI, for example, ADI instruction in the RISC based systems. There's ADI. Here you can use with the ADD opcode in the CISC based systems. So this can be either 0 byte could be used inside the x-axis instructions, because if you are using register addressing mode, then you are using 2 registers. There is no need for the immediate or constant data. So in this case, it will never use this byte. However, on the other hand, you can, if you are using immediate byte, then you require either 1, 2, 3, or 4 byte information or immediate value. So if you count out all these bytes, there are 4, 2, 6, 7, 8, 18, 4, 12. Then we have 4 more. So total there are 16 bytes. Just remember, in total there are 16 bytes. Now, if we are using all these 16 bytes, then I'm not sure, it's not possible, because here you can see only the maximum allows the Intel x86 allows maximum of 16 byte lengths. It's not more than 15 byte length. It's not more than that one. So from the diagram we can see that there are only the instruction can be 16 bytes long, up to 16 bytes. However, actually the x86 are Intel, for example. Why we use x86? Because there is like 286, 386, Pentium 1, Pentium 2, 3, 4, whatsoever you can call it. Then we have 80286, 8088, 86, 85, and so on. So that's the reason we use call, after that they are being called, all the whole family of processors is being called x86 and so on. So the prefix bytes are not the opcode expansion prefix, as we discussed there. They can be used. They are special bytes to modify the behavior of the existing instructions. So we will see when we are going to use these instructions. Maybe this will not be covered in this lecture, because it's a very huge topic, and the instruction encoding is more complex here. So within this lecture, maybe we cannot cover that one, how we can use that one, the prefix bytes. However, we will try to cover all the topics or everything related to this general instruction format. So this is an overview of the x86 instruction format. So we have 4 prefix bytes. This number of bytes is like, this can be either 0 or 1, means either we can use all 4 bytes, or we can use 1 byte, 2 byte, 3 bytes, 4 bytes, means maximum is 4 bytes. So 0 or 1 means either we use or we don't use this byte. So if we use this byte, it will be 1 byte. If we don't use it, it will be 0 bytes, and so on. On the other hand, here you can see we have opcode. This should not be 0 or 1, it should be 1 or 2. And then we have the MOD-REG-RIM byte, we have SIP byte, we have displacement byte, and we have the immediate byte. So here, this is the most general format. So in the opcode, it can be 1 byte, it can be 2 bytes, and then we have MOD and RM byte. This should be 1 byte here. So this MOD and RM byte is further subdivided in the different bit patterns. So we have 2 mod bits. Here you can see 2 mod bits. We have register or opcode 3 bits, and then RM bits. So 0 to 2, they are called RM bits. 3 to 5, these are called the register or opcode bits, and 6 to 7, these are called the mod bit, the mode bits, we can call it. So these are called the mode bits, which mode you are using or addressing mode you are using. However, the other byte is called the scale index byte. In the scale index, when you are using scale index mode or addressing mode, we have the scale, then we have the index, and this one shows the base, which base address you are using. So which index address, which is the register, or which is the register which is using index, what is the base, and what is the scale. So as we saw that scale can be 0, 1, 2, 4, and so on. So what type of scale you are using, definitely you have to represent it with the immediate value and so on. So this is the very general format. Now we will take a very closer look on each of these bytes, like opcode byte, MOD-REG-RIM byte, and SIP byte, and all the other bytes. So the instructions, they have the combination of following these prefix: instruction prefix, opcode, MOD-REG-RIM, SIP, address displacement, and immediate value. So we have discussed everything almost, that what is the purpose. So opcode operation, what type of operation, addressing modes or operands. So MOD-REG-RIM defines either addressing mode or what type of operands are being used. In the scale indexing mode, addressing mode when we are accessing the arrays, and address displacement for addressing the memory when you are going to refer to the variables, or maybe you are going to I say that when you are going to perform jump or other instructions, for example. So address displacement and so on. So what is the address displacement? Here we'll discuss. When we are talking about the address displacement, actually it is nothing but an address offset. Means we know that all memory is divided into segments. We have the code segment, data segment. In case if we are using the segmented addressing, means segmented mode, we're not using any flat and so on. So these segments are given a name, and we are using the offset. So we have actually the offset byte, offset information. This offset is nothing but the displacement within the segment. So it could be relative address, like 8-bit value used for jumping forward or backward from the current location of the code segment when we are going to use the labels and so on. Or it could be a location of a variable, like in the data segment, so a memory address of the variable. Or it can be a far reference, like we want to refer either code or data in other segments and so on. So this is the displacement which we are talking about here. These are the examples. So here you can see the displacement. For example, if I write jump next, actually next is nothing but address where we want to jump. So when next is a label in the current code segment, next is nothing but an address in the current code segment, and we are going to jump there. After that, we have the ADD EAX comma variable, for example, and what we are doing here, that we are going to access the current variable or current data segment, and variable 1 is nothing but the address inside that data segment. And the next instruction is, for example, sub BX. So this one is 32-bit register. Here we have the 16-bit register. Maybe you are using 8-bit register. So here is variable and ECX, for example. So variable is 16-bit variable in the current code segment, and ECX is an index register. So you can use this one to access the contents from the memory and so on. So these are the examples how you can displace within the single code, a single segment, or from one segment and from another segment. So this is the way you can move between a segment, or maybe you can access the other segment and so on. So that is actually the displacement which we are using. And we know that there's another thing which we are going to use is the immediate values. Now immediate values are nothing but we are using the constant value that is immediately available inside the instruction. So this is the constant which is used directly inside the operation. For example, here we use ADD EAX 7. ADD EAX 7. So this 7 is the immediate value, and there are no variable names, no source registers or nothing. We have only the destination register. This register will be, or the 7 will be added with EAX, and again register will, the result will be stored inside the EAX. Then next instruction is, for example, you can see compare AL EDX plus 10. So this 10 is a constant. Shift left AX comma 4, this 4 is a constant. So there are so many instruction formats where you require a constant value. So this is called the immediate addressing, where you are going to use a not immediate, but here in this case we got immediate addressing, and this is the immediate value. This is the constant value, but this is not called the immediate addressing, and so on. Okay, now we are going to start with the instruction prefix. This instruction prefix is used to specify options for the instruction execution. So I will just give you a very brief introduction what is instruction prefix. However, in this lecture we are not going to discuss in detail about the instruction prefix, the 4-byte instruction prefix. However, we will discuss all the other general formats of the instruction and so on. So they specify the options for instruction execution. Here you can see when we execute string operation like move as, scash. So all these instructions, the prefix is used to indicate that operation should be repeated. For example, repeat equal, the prefix is set to F3. For example, all these instructions. Repeat not equal, the prefix should be F2H. So this is 1 byte prefix. Then after that we have some values that indicate the memory segment that should be used instead of the default segment and so on. For example, ES prefix is set to 26, FS is set to 64 and so on. So these are the instruction prefixes, very short introduction. And this instruction prefix is, there's another example. Here you can see that we can use it, change the default data size for an instruction. For example, 32-bit to 16-bit or vice versa conversion if we are using, if we want to change. So the prefix will be set to 66H because sign extension, and we are using sign extension and so on, the extending the bytes from 16 to 32-bit and so on. So similarly, to change the size of the default address, we will use the 67 prefix. The lock shared memory, to lock shared memory, for example, if you want to lock shared memory, so the only this instruction has access. So if you want to change the default address size for an instruction set, set the instruction prefix to 67. If you want to lock the shared memory, so the only this information can be accessed by that, that only that instruction has to access that memory portion, then we can set the prefix to F0H and so on. Now this was the very brief introduction about all the bytes which are being all the portions of the instruction that we are using. Now, as I told you, we will only discuss the general instruction format. Here you can see there are two basic opcode sizes inside the x86. The standard opcode is 1 byte opcode. So the standard opcode is 1 byte opcode. It can be 2 bytes. So 2 byte opcode consisting of, for example, 0FH opcode expansion prefix byte. It can have the second byte, then specify the actual instruction. So in case if there are 2 bytes, then the first byte will have the 0FH and the second byte will contain the expansion, the actual information. So here we will not go to the more multiple bytes. We will discuss very simple what is inside the 1 byte opcode. So the x86 opcode bytes are 8-bit equivalents of 3 byte field that we discussed. So for example, if we are using the 8-bit opcode byte, then this will provide this provides up to 512 different instruction classes, for example. Although x86 doesn't yet use them all, still most of them they are available. Now there are so many other bytes that we have to discuss here. So possible possible combination is, for example, 512 different instruction classes, but it's not possible to use all of them. Still, most of them, they are available. And even if we are not using all of them, still this is called the complex instruction set computer and so on. Now, for example, we are going to use the ADD instruction, ADD Instruction Opcode. So the bit number 0 marked as S, this is called the size bit, just remember. So actually this one is, so there are 2 and 4, 6, 7 and 8, so they should be, for example, 0, 0, and simplify we can write them 0, 0. So ADD instruction operates upon that this is the size on which operands it is going to operate. So on which operands we are going to perform ADD operation. If S is equal to 0, then the operands are 8-bit registers and memory locations. So this specifies the size. Either we are using 16-bit or 8-bit, 16-bit or 32-bit operands. These operands can be registers, these operands can be a memory location or the combination and so on. If S is equal to 1, then the operands are either 16 bits or 32 bits. So in case of 32-bit operating system, the default is 32-bit operands, so S should be equal to 1. So S should be equal to 1. However, to specify 16-bit operands under Windows or Linux, you must insert the special operand side prefix byte in front of the instruction. So if you want to use 16-bit operand under the Windows or Linux, you must insert the special operand size prefix byte in front of the instruction. However, here you can see, for example, if we have so this whole all these 6 bits is, when all of them they are 0, 0, they mention that this is the ADD instruction, and D is the direction, S is the size. So now we have already discussed about the size. Now we are going to discuss about the direction. So bit number 1 marked D specifies the direction of the data transfer. If D is equal to 0, then this destination operand, whatsoever the destination operand you are using. So we have source operand, we have comma. So this is destination operand, and this is the source operand. So if D is equal to 0, then the destination operand is a memory location. For example, if we say ADD EBX comma AL, so destination operand EBX is the memory address. If D is equal to 1, then the destination operand is registered. Destination operand is a register. So if D is equal to 1, this should be registered. We are not sure that this can be memory or the register here. It must be mentioned by the MOD-REG-RIM byte and so on. However, there's one confusion here, that if mod bit is 1, D is equal to 1, and if you are using the register addressing mode, then what will be the opcode? Or if you are using the in case of register addressing mode, for example, if I say CL comma AL, in this case we don't have any addressing mode here, means we don't have any memory location, like in either in the destination, either in the source operands. So what should be the opcode for this one? In that case, there's confusion. However, in that case, it will consider D as a 1 in the XSS ADD instruction opcode, ADD instruction. Here you will see that the mod register RM byte, inside the mod register, this is the mode. Actually, I'm sorry, means we are calling it mod, but it's actually it is the mode, which mentions the mode of in which mode is going to operate, like the either it is a register addressing mode, either the other immediate addressing mode, or other addressing modes. So this is called the mode register RM byte. It specifies the instruction operands and their addressing modes. So actually, technically, what we call registers, they don't have any addresses, but we apply them the term addressing mode to the register. We call it register addressing mode, even though they don't have any addresses. But here you will see that all the registers, they have the special number, and that number can be used, or that number is used as an address. So this mode is two bits. Register or opcode, this is the 3-bit. or RM bit pattern is 3 bits and so on. So RM field combined with mode specifies either the second operand in a 2 operand instruction, the second operand in a 2 operand instruction, or the only operand in a single operand instruction like not or negative and so on. So it mentions that either the second operand in a 2 operand instruction mode, what is the second operand and so on. This specifies the first operand and so on. So we have the D bit. If the D bit is set, then in the opcode we know that this is the direction bit, which operand should be the source and which should be the destination. If D is equal 0, then whatsoever inside the register you are going to mention here, inside here, it will be used as a source, and if D is equal 1, whatsoever the register you will mention here, it will be used as a destination register and so on. So here you will see that we are using the mode register RM byte, and there are different values of mode 00, 01, 10 and 11. So you have seen the RM, it will mention the what type of source or destination byte destination you are using, but mode mentions the register either if it is 00, then register in direct addressing mode, or SIB with no displacement when RM is equal 100, or displacement only addressing mode when RM is equal 101. So this mode bit is used in combination with register or the RM bit pattern. For example, if it is 1-1, then it will be used for the register addressing mode when we are going to exchange information between or perform any operation where only source and destinations are registers. In case if it is 10, then 4-byte sign displacement follows the addressing mode style bytes and so on. So addressing mode style whatsoever you are using, and there will be 4-byte displacement, sign displacement will be used. If you are using 01 for the mode, then it will use only 1-byte sign displacement. You will see in the examples later on. However, the third part is called the register part or register field. This field specifies either the source or destination register. It depends on the direction. If as I told, if D is equal 0, this register is a source. Whatsoever the register number is mentioned here, it will work as a source register. If D is equal 1, this register field, register bits in this field, whatsoever the bit pattern you are mentioning, it will work as a destination register. So it depends on the D or the direction. So next we are going to move what should be the values of all these registers. Now, as we know that we have byte, 1-byte opcode, and we have 0-bit size and D bit for the destination for the direction. This is 1 bit, this is 0-bit. Now if we are using the 32 bits or 16 bits, then size should be 1. If we are using 0, then it should be 8 bits. So in case of 8 bits, these are the registers whose values will be used. So you can see if it is 000AL, 001CL, 10DL. So you can call it like 0, 1, 2, 3, 4, 5, 6, 7. So these are the values from 0 to 7. So if you are using 16-bit, then you will have to use this 0 will indicate inside the register. 0 will indicate AX register. If you are using 32-bit mode, then this 00 will indicate EAX register and so on. So register field specifies source or destination register, and this can be the value because this is 3-bit field. So these are the three bits inside the register or opcode register area, which will mention that which register you are using. If we are using mode and RM byte, and for example, if mode is equal to 00, if mode is equal to 00 and RM byte is equal to 00, if mode is equal to 01, so it depends on the mode which mode you are using. If you recall all those modes, then here we have displacement of 4 signed bytes, 1 byte, and this one, and here is the register addressing mode and so on. So in this case, for example, if you are using mode is this one, whatsoever the mode you are using here, in addressing mode with the 8-bit displacement fall in the range like 127 minus 127 to 128 minus 128. So for example, here in this case, the addressing modes with 8-bit displacement, it will fall, this displacement will fall in the range of like minus 128 to plus 127, and it require only a single byte displacement after the opcode, so it is really faster. On the other hand, in the second, like this one, register addressing mode, so the size bit in the opcode specifies like we're using 8 or 32-bit register size, as we mentioned. To select 16-bit registers register, it requires a prefix byte. So in case if you want to use, because it only mentions either 16, if s is equal to 0, you can use 8-bit. If s is equal to 1, then you can use 16 or 32. However, by default they are using 32-bit registers. If you want to use 16-bit register, then you have to use the 16-bit from the prefix byte for the register size and so on. The third one here you can see, if you want to use 00 and 100 in the addressing mode or like RM, then this will be the third type of addressing mode that will be selected. That is called the scaled index addressing mode. So in case of scale index addressing mode, the SIB byte will be added. SIB byte will be added inside the instruction. So we will discuss what is inside the SIB byte. So these are the different addressing modes which will be used. Then the fourth addressing mode will be like here, if mode bit is equal to 00 and RM bit is equal to RM bit patron is equal to 101 and so on, then the fourth addressing mode will be used. So it is the EBP plus displacement. So this is called the displacement only addressing mode. So Intel has decided that the programmers can use EBP plus displacement 8 addressing mode instead with its 8-bit displacement, which is set equal to 0 and so on. So this is the fourth one. If you want to use this type of addressing mode, you can use that one. So for that purpose, the mod bit should be 00. So sorry, the mode bit should be 00 and RM bit should be 101 and so on. So now we are going to discuss about the scale index byte layout, and as we know that if we are using the scale index addressing mode, as we know if we are using the RM plus mode and RM byte combination, and if we select the scale index addressing mode, then this SIB byte should be used, and this byte should follow the MOD-REG-RIM byte. After that, this should be there. So the mod field in the mod register RM, still it specifies the displacement. So displacement can be 0, 1 or maybe 4 bytes and so on. So the mod register RM and the SIB bytes are very complex because Intel used 16-bit addressing circuitry in the 32-bit mode rather than simply abandoning the 16-bit format in the 32-bit mode and so on. So there are good hardware reasons for this one, but the end result is that complex scheme for specifying addressing modes in the opcode. So it's very complex in the opcodes. However, we have simplified Intel has simplified the hardware. This is the layout, the bit pattern for all the whole SIB byte. In the SIB byte, first we have the scale. So scale values can be 0, 0, 0, 1, 1, 0, and 1, 1. If we are using 0, 0, then index multiply by 1, multiply by 2 for the scale value 0, 1. So index multiply by 2, index multiply by 3, index multiply by 4, depends on the scale value which we are using here. Then we have the index. So for example, which register holds the index? For example, if it is 0, 0, then EAX holds the index. 0, 1, 0, 1, 0, 1, 1 This one is illegal if we use 100. Why it is illegal? Just see what is on the 100 register and for what purpose that register can only be used. 101 is EBP, 110 is ESI, and so on. However, if you just come to the base register, it mentions which base register should be used if we are using the scale index addressing mode. So here, base, for example, if it is 00, then we have the EAX and so on. At this point, if it is 101, for example, then displacement only if mode is equal to 00, and EBP means then EBP if the mode is equal 01 or 10. Otherwise, for 110 or 111, it will use ESI and EDI and so on. So here you can see we have all the bit patterns, what type of scale n means a scaling factor will be used, which register will be used as index, which register will be used as a base, and so on. So everything should be mentioned here, that if we are using the scale index mode and so on. After that, these are the, for example, if mode is equal to 00, mode is equal 10, mode is equal 01, mode is equal 00, and base is equal 101, and so on. In this case, so here mode is equal 00 and RM is equal to 100, then we are using SIB, and displacement for 01 and 100 RM field, they will use the displacement of 8 bits, or in this case they will use displacement of 32 bits, and so on. So in each scale index addressing mode, the mode field in the mode register RM byte specifies the size of the displacement. It can be either 0, 1 or 4 bytes, and so on. If mode is equal to 00, here you can see it will use 32-bit register plus EAX multiplied by n, and so on. So it can use either EAX, EBX, ECX, EDX, EBP, ESI, EDI, and so on. And if the mode is equal to 01, then we will have displacement plus register 8-bit and plus the EAX, EBX, or whatsoever the register multiplied by n, which is mentioned inside the scale pattern, and so on. Similarly, for this mode is equal 10 and 00, and base is equal 101, so on. So here you have gone through. There's a huge detail about all this, theoretical detail about this encoding. We will not go in more detail, and we will just continue what is happening here actually when we are performing ADD instruction or some other instructions. So this opcode can be, this ADD opcode can be decimal either 0, 1, 2, or 3 depending on the direction and size bits. So this byte, whole byte, can be whole 0 if the size is, for example, 8-bit. Direction is if the destination register or source register which is being selected by the mode and register mode RM byte. So it depends. So if D is equal 0, so we are adding from register to memory, otherwise from register to memory if D is equal 1. So otherwise if D is equal 1, we are adding from memory to register, and so on. This is the size as we already discussed. So how can we encode various forms of the ADD instruction? This is the main question. So we will start with the basic. CL and AL, this is these two are 8-bit register. This one is 8-bit, and both are 8-bit registers. Now we know that this 0, 0, 0, 0, and this direction bit is 0. For example, we are not using any memory, either we are not using from memory to register and register memory, and so on. This is the direction bit which actually shows that from which direction you are using, from register to memory or from memory to register. So in this case we are not using any register, any memory address or memory location, and so on. So here is the confusion. In this case, what should be there? Either it should be 0 or it should be 1, because in case of, as you just go into the previous slide, If D is equal means 0, then we are going from register to memory, means the destination should be memory. Otherwise, if D is equal to 1, we are going from memory towards the register. There is a problem. So in this case, there is nothing. So this can be either 0 or this can be either 1. However, here this 0 indicates that we are using the 8-bit values, 8-bit registers. This mode should be 1-1 because we are using the register addressing mode. So the 1-1 indicates that the RM field is a register and so on. So RM field shows the register. Even the register field shows the register also. So here this field along with the D bit in the opcode indicates the source field in the AL register. It can show the destination field in the register. So this can show that if it is 1, then it shows the destination register as a AL. Otherwise, so if you want to show destination as a AL or source as a AL, whatsoever, depends on the direction bit. So on the other hand, we have the, so if it is 0, 0, 0, it means we have the destination register AL bit. If it is 0, 0, 0, 1 in the RM, it is CL, and this one is AL. It is shown as an AL and so on. So if I encode, if I just combine all these bits, for example, all these zeros, 4 bits are 0, so in hexadecimal this should be 0. If it is 0, if this bit is 0, then it should be 0. Otherwise, it should be 2. And if the direction is 1, for example, in this case, if we combine these 4 bits up to here, if we combine, so it should be 1, 1, it should be 12, 12, either whatsoever the direction is. In case of AL and CL, this should be C from here to here, and from this one to this one, it depends which one you are using. If you are using DL as a the CL as a source register, definitely here is the AL is the source register and CL is the destination register and so on. So it depends. If you are using direction is equal 1, then it should be mentioned here. So in this case, it should be in the first case, it should be 1. In the second case, it should be 8. Here in the first case, it should be C. Second case, it should be C. So there are two possibilities. It can be either 0, 0, C1 or 0 to C8. If the direction bit is equal to 1. Why there's a problem here. Interesting side effect of the direction bit and the MOD-REG-RIM byte organization is that some instruction can have 2 different opcodes and both are legal, as we call it. So for example, but however, we know that our register is a destination, so we inside the assembly, whenever you will right click and see the bit, it should be D is equal to 1. So for example, for the previous ADD instruction, you will always see 0, 2 and C8. You will never see the 0, 1, 0, 0, C1 and so on inside the assembly language when you just when you are going to see the hexadecimal bit pattern. So for example, encoding the mod CL comma L could be 00 C1s, and if D is equal to 0, if D is set to 1, then definitely we have to shift that one to the destination register is the CL, so destination register should be there, so we shift that one here. So it is called the so we just shift destination register here to show that the destination register inside the register field and so on. So that is a possible case, and I'm sure if you will just right click, you will see the 0, 2 and C8 and so on. So the possibility of opcode duality issue here applies to all instruction with 2 register operands. So it's possible if you are using register addressing mode, this is the possibility you will ever encounter there. Then if you are going to use 32-bit registers, in case of 32-bit registers, then definitely this direction bit should be there, should be set to 1. If you are using, so destination register should be here. There should be destination register. For example, destination register is equal ECX, so it should be 0, 0, 1, and this bit should be 1 because we are using 32-bit operands. Mode bit is going to show that we are using the register addressing mode, and RM field should be 0, 0, 0 is the destination byte. Destination field, sorry, the source field, it will show the source field. It should be 0, 0, so because we are using EAX. In this case, it should be, there are two possible cases. This case, first case can be 0, 1, and this case, the one which we are going to mention here, it should be 0, 3, C8, and so on. So this is the case when you are going to perform addition for 32-bit registers. And then if we just move for the displacement, so in this case, if we use displacement, as we have seen the displacement examples, in case of displacement, if you perform the add operation with the displacement, or maybe any register and so on, there will be one possibility. Nothing will change here. The one thing is we are using direction. So direction should be 1 because our destination is our the register. From memory to register we are going to pass, and mode is not the this mode. The combination of mode bit is equal 0, 0, RM is equal 1, 0, 1. It indicates that this is the displacement only addressing mode. We are using only displacement. There is no base involved, there is no index involved, nothing is involved, only base is involved. If we just go to the mod or the mode bit and RM bits, bit patterns, you will see everything there. Here it must show that what is the destination register here. For example, if there is EDX, we are using EDX, then EDX has the bit pattern 0, 1, 1, and this will show that we are using the destination field, that is the 0, 1, 1, and RM101 will show that we are using the displacement only along with the mode. Here we are not using the how can I say, the register addressing mode. In case of register addressing mode, it should have been 1, 1 here, and this bit must have shown that the source register. And this displacement is 32-bit. For example, displacement is 0, 1, 0, 2, 0, 3, 0, 4. I think this is now, if it is hexadecimal, this is 32 bits. 1, 2, 3, and 4. So these are the 4 bytes, so 32 bits. Assume that if we are using this one as a W, or XX, YY, sorry, YY should be here, and ZZ, for example. So these are the lower order bytes. This is the lower order byte, and this one is the higher order byte. So in this case, higher order byte should be there, here, and then lower order, then lower, and this is the lowest order byte. However, if you just go through the ADD instruction with the displacement, you will see here at this point, you will see that there will be lower order byte, because if you just right click on the instruction, so displacement can be any variable. If you are going to add variable with some EDX and so on, so there'll be address for this one. So this 32-bit value, or the displacement value, that will not be the address, that will be the displacement value inside the segment. So this is the lowest order byte, or lower order byte, then the next lower order, the next, and then higher order bytes. So it will be shown in this way if you are using the displacement addressing mode, or displacement only addressing mode with add instruction. Whatsoever the instruction, if for add instruction it is 0, 0, 0, 0, and so on, and for the other instruction they have different opcodes. So there are move instruction is different opcode, subtract instruction is different opcode, then other instruction they have their different opcodes. So you can use any of the instruction, rest will remain same, however the opcode field will differ. If that instruction is using the register addressing mode or the displacement addressing mode whatsoever, the rest will be same, however the first opcode will be different. So if you combine, if you different if you put different opcode here, then definitely rest of the bit pattern will be different. So it's not possible to have the common bit pattern for this encoded bit pattern for any of the instruction. Now here at this point, there's another example. If you are going to encode ADD EDI and the indirect addressing mode, register indirect addressing mode. So this register indirect addressing mode, for example, we have the information in EBX, or addresses inside the EBX. So this should be 00, indicates 0 byte displacement. In this case, it will show that we have 0 byte displacement, and now it will not be 101, it should be 001, indicates that the EBX register, the indirect addressing mode, or EBX, is the register which is holding the address. So this should be between, indicates that we are adding from memory to register field. So we are adding from here. We are adding from memory to the register. So RM field has the EBX value. So this is 011, and this one is the EDI register, and EDI register is a destination register, and here EBX is a source register, and this 011 indicates we are using the EBX register here. Now at this point, what will happen when you perform this instruction and right click, it will give you 0, 3 and 3B, because this one is 0, from here to here is 0, from here to here is 3, and up to here it is also 3, and here it is 8 into 10 and 11, so this should be B. So 0, 3, 3B, this is only 2 byte instruction. Previous was not 2 byte instruction. If you just go, previous is more than 2 byte instruction, 4 byte for displacement and 2 bytes for this one, so at least 6 byte instruction. If you just go here, go 2 into 4, and so this is 2 bytes plus 32 means the 4 bytes, 5 and 6 byte instruction. Okay, so now we are going to discuss about the new pattern where we are using the ESI plus displacement. This will give you the memory location from where we will transfer value whatsoever are add with the EAX. So we know that EAX is equal 0, 0, 0, and direction should be 1, because from here plus here whatsoever the value will be, this will give you the whole complete address from where we will transfer value to the register EAX. So EAX register is the destination register, and we know that along the direction bit in the opcode indicates the destination field is the EAX, and so on. So 8-bit displacement follows the MOD-REG-RIM byte, so displacement 8 should be here. In case of 32-bit, it should be there. So 01 in the mode bit, this mode bit indicates a 1 byte displacement. So we have the mode bit here, so there should be 1 byte displacement, and then you can see that whatsoever the 0346 access will be the encoded one. So just wherever I said mod bit, so it's not mode, it's actually the mode bit which we are using. The second one is if you are using the 32-bit displacement along with this one. For example, EBP and EBX, here we are using EBX. So this is the EBX, this one RM is the EBP, so it's 101, we use the EBP, and here is the displacement is 32 bits. So 32 bits is the WWXXYY, so this is the lower order byte, this is the higher order byte, and so on. And 9D will indicate we are using the EBP plus displacement 32, and it will combine and form the address from where we are retrieving the value, and we are going to add with the EBX and so on, the 32-bit register. Now the scale index mode, as we know that it is used to work with the arrays. For example, the base could hold the location of an array and the index, the offset of an element, and so on. So we have base plus index, or the displacement field is the name of an array, and so on, and the index is the offset of an element, and so on. So we can use scale index, and the base index, and the scale index, so on. So multiply the index register by a scaling factor 1, 2, 4, or 8 8 times to adjust the size of the operands of different types. So if we multiply 1, it's like byte type. 2 means the word type, double word type, and quad word, and so on. So if an array of type word requires the factor of 2, an array of double word requires a factor of 4, and so on, and quad word is there, and so on. So this is mainly, this scale index mode is used mainly to access the arrays where we are using the base plus index, and so on. So scale index addressing can use the displacement. Displacement is the nothing but the variable name, and then index, this is the offset. So actually this one work as a base. So here you can see it is a base, then we have the index, and then we have the scaling factor. So we have a scaling factor, we have base register, we have index register. So it can be displacement, index multiplied by base, or maybe base, index multiplied by n, or all of above. You can use any of the format. There are multiple formats for the SIB bytes or the scale index addressing mode. So here is the effective address calculation. We have the base register, we have the index, and we have the scale. We have the scale. So this is called scale index addressing mode, and we have displacement can be 1 byte, none byte, or 1 byte, or maybe 2 byte, or 4 byte, and so on. So effective address can be base plus index multiplied by scale and plus displacement. So you can calculate the effective address. This is the complete list. You can calculate any of the effective address, and so on. So here you can see the example. Here we have displacement plus EAX. So displacement is 32-bit. This should be here 32-bit. We have the now at this point we are using SIB, but the combination of SIB is different. So if it is 0, 0, so these two fields select the EAX register multiplied by 1 scale index. So 0, 0 is scale index 1 mode. This one indicates the EAX register. Here is the 32-bit register we are using. And 101 in the last bit pattern means the displacement only addressing mode. So displacement is here. Actually this is nothing but the SIB byte. This is the SIB byte, and this one is going to show that we are using register, and mode is equal the mode plus the RM bit pattern shows that we are using 32-bit displacement plus register multiplied by 8 mode. So this is the destination register. This destination register is 101. 101 is nothing but the EBP, if you just see the list, and so on. So this is the bit pattern. If you are using the displacement, so it should be 0, 0, 0, 0, then 0, 0, 1, 1, and so on. So this is the binary bit pattern that will be supplied towards the machine to perform any operation. And this is the another example. Here you can see we have the SIB byte. Mode bit is 0, 0, RM bit is equal 1, 0. So it means that we are using the SIB mode. So actually now this is used as a SIB mode. This will use the source scale index byte. So scale index and base so is 1, 0. So 1, 0 is nothing but we are using the multiply by 4. EDI is equal to 1, 1, 1, and base is equal to 0, 1, 1. So base is equal to 0, 1, 1 means we are using EBX. So EBX, EDI multiply by 4. It's everything done by the SIB byte. Now we are using mode is equal to 0, 0, and RM is equal to 1, 0, 0. So it is we are using the SIB mode. Or this one is a register is called the ECX register 001 in 32 bits. So it is ECX register. So if you just combine everything here, you will get the opcode like 03, 0C and BB. This is the opcode which we are using here, which will be considered here in the which will be supplied to the processor to perform this type of addressing operation. Now, in case previously you have seen all the other addressing modes, most of the addressing modes. Now, for example, if you want to use immediate, then this is the byte, this is the bit that should be equal to 1. So this first or the higher order byte of this opcode should be 1. It indicates that this is the immediate, indicates that this is an immediate mode instruction. Now, what is the instruction? This instruction should be available in the next bits. So indicate that we have the ADD instruction, which is using the immediate addressing mode. Now, X, this D, there should be X, it should be 0 when constant size is equal to S. For example, if S is equal to 0, we are using 8-bit operand, so constant should be 8 bits. S is equal to 1, it means the operands are 32 bits, so constant should be 32 bits. However, if D is equal to 1, then the constant, so we know that this register here, this is added with the opcode. Definitely it will just extension 00 for the ADD immediate instruction. In this case, this will not work as a register. This will work as a part of the opcode. That is the reason we call this register opcode pattern, or register opcode 3 bits. In case if this X is equal to 1, then the constant is 1 byte operand, that is sign extended to the size of the operand and so on. So here the optional 1 or 2 byte displacement as specified in the MOD-REG-RIM field will be added here at this point. So mod is equal to 00 and RM is equal to 10, so it specifies the destination operand, and then so at this point there will be a constant, either it can be 16-bit or 32-bit constant that will be used here. Now you can use any of the constant and you can see what will be the opcode, the bit pattern for this ADD immediate instruction. So you can use any of the register, you can add any of the value and just see what will be the value. Now, this is the way you can encode all the instruction. However, you can see what are the opcodes for other instruction like move instruction, increment instruction, and so on. So this was the very short or brief introduction about the addressing modes, and now we are going to summarize that what we did in this, what we discussed during this last lecture. We discussed about the how encoding the real x86 instructions, the introduction. Then we saw the instruction format and the opcode sizes, then ADD instruction opcode, then how can we encode x86 instruction, and what are the mod register, this mode register RM byte. So this is the mode register RM byte and so on. And what is the register field in this mode register RM byte? Then what is the bit combination to form the addressing mode for the mode register, mode RM byte and so on. Then scale index byte that we have used to see how can we, if we use the scale index addressing mode, then to access the array elements, then we use the SIP byte, and SIP byte has the scale, then index, and we have the base and so on. So all these bit patterns. Then we have seen the layout for the scale index addressing mode and so on. Then all these are the instructions, instruction formats with different addressing modes for the ADD instruction. So we have seen most of the instruction formats, even though we have never used all of them in our assembly programs. However, we have considered them to see what should be the encoded bit pattern when we are using ADD instruction with different addressing modes. So this is end of the lecture, and there is no further lecture, so I will not say till next lecture. So this is end of the course. Wish you all the best, and inshallah hope to see you and maybe in other subject or maybe in other class. So till then, Allah Hafiz.